I'm Ryan Urbanowitz, and this is part 9 of Machine Learning Essentials for Biomedical Data Science. In this short video, we'll discuss machine learning pitfalls and solutions, reviewing the ones we've already covered, as well as covering some new ones. Some of these pitfalls will be relevant to any type of analysis, even if it doesn't involve machine learning. Here's a quick reminder of the parts making up this video series. In the last video, we covered post-analysis in a machine learning analysis pipeline. Let's begin here by reviewing the machine learning pitfalls that we've directly covered so far in this video series. These include bad data, where issues with data quality can wreak all kinds of havoc downstream. Class imbalance, which can make it difficult for some algorithms to effectively train, and requires us to be careful in evaluating and interpreting our results. Data leakage, where data that shouldn't be included in training was included. We also talked about different kinds of missingness in data, and how this can impact how we prepare data, including cleaning and feature engineering. And of course, we covered overfitting, where an algorithm ends up memorizing training data rather than effectively capturing generalizable associations. And lastly, we covered sample bias, where the instances we collect or partition to make up our training data end up not being representative of the larger population or dataset. Beyond those pitfalls, a number of others came up indirectly that are worth highlighting here. First, as a researcher, for example, a clinician or biologist, if you lack the quantitative expertise, another pitfall might be failing to talk to a statistician or data scientist early on in the development of a study. Ideally, if you intend to apply a machine learning or statistical analyses, it's ideal to consult with an expert before the experimentation or data collection phase to ensure that you have enough data, as well as to make sure you gather all the information possible to maximize your chance of success. Of course, in practice, this isn't always possible or even practical. For example, if you are beginning a research study using existing data, let's say from an electronic health record database. Another pitfall might be failing to take time to clearly understand and describe the problem or goals of the study, or failing to conduct an exploratory analysis, instead diving right into modeling without understanding the specific quality and nuances of the data in hand. In line with this is failing to look for outliers, which may point to errors in data collection or require data transformations in order for some modeling algorithms to perform well. Furthermore, we alluded to the possibility that removing features that are strongly but not perfectly correlated can be risky, given that it's possible that crucial information might still be lost, leading to poorer model performance than might have been achieved. Another potentially big pitfall is failing to consider the assumptions being made by the algorithm or algorithms and respective hyperparameters used for each. This can lead investigators into making incomplete or incorrect conclusions. A simple example of this might be relying on algorithms that assume linearity, while the underlying association is much more complex. Without considering the implications of this assumption, a researcher might incorrectly conclude that there's no reliable signal in a given dataset. Another common pitfall is failing to look beyond default algorithm hyperparameter settings by using some form of hyperparameter sweep. And as a last indirectly covered pitfall, failing to use appropriate metrics for model evaluation. We saw a basic example of this when using standard accuracy to evaluate a model with a large class imbalance. Now let's move on to discuss some additional machine learning pitfalls that haven't really come up thus far in this video series. The first one deals with the point that just because something is representable in a model doesn't mean that it's learnable. To try and clarify, just because an algorithm is theoretically able to represent some target function or solution doesn't mean that it will be able to learn that representation from the data. As a more accessible example, let's go back to decision tree algorithms, which technically should have no problem representing interactions between features in a model. However, since they learn by splitting one node with one feature at a time, the model might not be able to learn that interaction, especially if there is a large number of features in the dataset. A solution here is to be aware of how an algorithm represents knowledge, as well as how it goes about learning. Also, try to include algorithm strategies that are less susceptible to falling into local optimas. Algorithms that are susceptible to this would include algorithms that train in a greedy manner on data and can't find their way out of local optimas to be able to find or get closer to some global optima. We learned about local and global optimas in the video on neural networks, which was part 6 of this series, where there we called them local and global minima since we were trying to minimize our loss function. Our next machine learning pitfall points out that model simplicity does not always imply better generalizability. Throughout this series, we've often emphasized the importance of model interpretability, which is generally associated with a model being simpler. But of course, there is such a thing as too simple. Basically, the problem here is taking Occam's razor too far, where we focus too much on simplicity at the expense of efficacy. One way this can lead to an error is if we have two models yielding the same training accuracy. We might presume that the simpler of the two will have better testing accuracy. However, this is not necessarily going to be the case. The solution here is simply to prioritize generalizability over simplicity whenever possible. Also, make sure to try out various machine learning algorithms on a given problem, as well as ensembles of models, to see if they yield significantly better generalization performance, even potentially at the expense of being more complex and less interpretable. And lastly, avoid simplicity for its own sake. Our next pitfall is data dredging, also known as data fishing, data snooping, and p-hacking. I love this quote related to the topic of data dredging. If you torture data long enough, it will confess. The problem here is that if you resample and reanalyze your data enough ways, eventually you're more likely to observe some associations purely by chance. We're more likely to do this when we failed to first devise a specific hypothesis and instead are openly fishing for results. This is also a problem if we fail to acknowledge the number of analyses we've conducted on the same data, or that a found association could always have just been the result of random chance. Data dredging is another possible source of replication failure, which we talked about at the end of the previous video. You might find an association by chance after data dredging, only to find it doesn't replicate later, since it was just a sporadic random association. The solution here is to define a specific, testable hypothesis targeting a primary outcome measure prior to conducting analysis. And if this isn't possible, or you want to conduct more of a discovery analysis, make sure to statistically account for multiple tests when establishing the significance of findings. The next pitfall is confirmation bias. This is a tendency to search for, interpret, favor, and recall information in a way that confirms one's pre-existing beliefs or hypotheses. In the context of statistical analysis or machine learning, this could occur, for example, when the data analyst is briefed in advance to expect a particular finding or conclusion, and this bias improperly influences the analysis that was conducted or not conducted. The solution here is to avoid setting out to prove a predefined conclusion. Rather, test defined hypotheses in a targeted way, and be mindful of your own pre-existing biases. Another pitfall that is probably just as well known as overfitting is mistaking an association for causation. Specifically, this involves believing that an observed association or correlation in data implies a causal relationship. As a silly but vivid example of this, here's a plot showing the divorce rate in Maine over the years, given as a red line, compared to the per capita consumption of margarine over the same time period. While there certainly appears to be a correlation between these two variables, a reasonable person should find it highly unlikely that one variable caused the other. As we already mentioned in the first video of the series, we should always be mindful that machine learning is designed to model associations, and thus when we find associations, we should never assume that they are causal, since these associations are candidates for causality at best. Yet another pitfall involves failing to consider confounding variables. The problem of confounding is when an unknown or unaccounted for feature is correlated with two features of interest, resulting in an incorrect perceived relationship. So for example, we observe that the rate of ice cream consumption is correlated with the number of sunburns. Like in our last slide, while these are associated, it wouldn't make sense to a reasonable person that one of these would cause the other. Indeed, there is another confounding variable, in this case the hot temperature of the sun, which is causally driving the correlation between the other two variables. Since machine learning is typically not focused on causality, the pitfall of confounding variables is not always addressed. However, when we are interested in ultimately tracking down causality after machine learning modeling, taking confounding variables into account may be very useful. We might address this issue either at the level of the experimental design, where we're careful to gather potential covariate features in our data. We might also assemble our dataset such that we match instances with different outcomes by expected or suspected covariates in order to try and remove their effect. In clinical studies, common covariates include age and sex. And further, we might try to apply machine learning modeling with and without covariates in an effort to evaluate their influence on model performance. And this brings us to cherry picking, the last pitfall we'll discuss here. Here, the problem is simply selecting results that fit your claim or bias while excluding those that don't. Cherry picking can either be deliberate or involve some degree of negligence on the part of the analyst. For example, if you're the recipient of data that has already been cherry picked and you didn't take the time to explore it or learn exactly how the data was collected or pre-processed. The solution here is to know where your data comes from and how it was pre-processed. And of course, don't be dishonest by deliberately manipulating data. Thank you for joining me for Part 9 of Machine Learning Essentials for Biomedical Data Science. In the next video, we will conclude this video series by covering a rapidly emerging subfield of artificial intelligence and machine learning, and that's automated machine learning, or AutoML. If you enjoyed this video, please like and subscribe to follow my future content.